Hello everyone. In this video, we're going to learn about different ways to test for the presence of heteroscedasticity in our model. Now, we've reviewed the method of computing robust standard errors. And this solution is very powerful because it helps us, the standard errors that we thus construct are valid. They help us construct t-tests and f-tests and do our statistical hypothesis, whether or not there is heteroscedasticity in the model. But oftentimes we'll actually be interested in going ahead and checking if there is heteroscedasticity in our data set, because then we can very confidently apply our robust standard errors, so on and so forth. So we're going to learn of a couple of tests that we use in practice to do this. So let's start with the first one. Now, our usual linear model is given by this expression. Y is given as a function of x1, x2, and so on, up to, my apologies, there's just a minor typo here. We're going to go from beta 1 x1 up to beta k xk plus the error term. Now, we're going to construct a test for heteroscedasticity such that the null hypothesis says there is homoscedasticity, and the alternative says that the null is no longer true, that there is no longer homoscedasticity, which means there is heteroscedasticity. So our null hypothesis is that assumption 5, MLR5 is true, meaning the variance of u given x is a constant, that is homoscedasticity holds. Now, we can rewrite this expression in a slightly different way, which allows us to go ahead and do this test in practice. Now, we can rewrite the variance as, so if you're given variance of any variable x, right? It is actually nothing but expectation of x squared minus expectation of x the whole square. So in a similar way, variance of u given x is just expectation of u squared given x minus e of u given x the whole square. Now, when assumption 4 holds, e of u given x is just 0. So the variance just boils down to expression of u squared given x. So in that case, the null hypothesis of homoscedasticity just boils down to the expectation of u squared given x being a constant. That is, expectation of u squared, the conditional or unconditional expectation, should just be the same number, a constant. It does not vary with the x's. So my null hypothesis tells me that the u square term does not have any relationship with the x values. So to test for this homoscedasticity violation, we only have to go ahead and test if u square is related to one or more x values. So let me repeat. The null hypothesis tells me that, so my null hypothesis is that e of u squared given x is a constant. So the unconditional variance and the conditional variance are just the same. They're just a constant. They don't depend on the x values at all. Sorry, unconditional expectation or conditional expectation. So essentially, the null hypothesis is that u squared is unrelated to the x values. So all that we have to do is test if u squared is related to x values or not. So what are we going to do? We're just going to take u square and express that as a linear function of all our x variables. So I'm going to write u square as a function of all my x variables, and I'm just going to run a regression to check that. So I'm going to regress u square on all of my k x variables. And what I have to do is that if u square is unrelated to any x variable, then all of the slope coefficients have to be jointly 0. If delta 1, delta 2, and so on up to delta k are all 0, then it means that my u square is unrelated to any x variable, and therefore, if the null is true, homoscedasticity holds. So now testing for heteroscedasticity just boils down to running a regression of u square on all the x variables and checking for the joint significance of that regression. And we could just use F statistics or the LM test to do this, to test this null hypothesis. So how does it happen in practice? Well, we don't know U square, but we know U hat. We can compute the residuals from our regression. So we first compute those residuals, the U hats, take a square of that, and then regress U hat square on all of your X variables. And now all that is left to do is we just have to test the null hypothesis that delta 1 equals delta 2 equals up to delta k. All of these coefficients are jointly 0. And we could use an F test or an LM test to do this null hypothesis. If we were to use an F test using the R square version of the test, your test statistic is given by this particular formula, where the larger the test statistic, the larger your F value, and a larger F value is generally evidence against the null. So we could compute an F statistic and do an F test. We could also compute an LM test statistic and do an LM test. Now, this LM version of the test is called the Breusch-Pagan test for heteroscedasticity, also called the BP test. So if we end up finding a large F stat or a large LM stat, or in other words, if the p-values associated with each of these test statistics is a really tiny number, well, that is evidence against the null. So in those situations, we reject the null hypothesis. Now, if you end up getting a very small test statistic and therefore a large p-value, that is then there is no evidence to reject the null hypothesis. If we don't reject the null, we're believing that the null is true and we're going with the homoscedasticity story. So this is one of the simple tests that we use, the Breusch-Pagan test for heteroscedasticity. The particular example that we've reviewed here assumes that U hat square depends on all the X variables. If there is some reason to suspect that the U hat square depends only on a certain set of X values and not every X variable, variables, not values. If we suspect that it only depends on a few X variables, we just include those in our U hat square regression, and we adjust our null hypothesis accordingly and modify the number of restrictions accordingly, but then the rest of the process is the same as before. Let's review a very quick example here. So we're looking at housing price equations. So we're regressing housing price on the size of the house, the size of the ground, the square feet of the house, the number of bedrooms in the house. So in the first version of the regression that we run, if we compute, if we do the Breusch-Pagan test for heteroscedasticity, the p-value for such a test, it's 0.002 if you use the F statistic. If you use the LM statistic, it is 0.0028. So if we are doing a test for heteroscedasticity, either the F test or the LM test are giving us very tiny p-values, which is evidence against the null. So we're rejecting the null and we're concluding that there is heteroscedasticity in the data set. Now, we've seen that when we do a log transformation in our data, the log transformation is one of the is a very useful tool because it helps us tackle these problems of heteroscedasticity and ensure that the error distribution aligns more with homoscedasticity. So if we were to do that, if we were to transform a dependent variable and a couple of independent variables into their log versions, note that we're not transforming the bedrooms into the log expression because then the interpretation doesn't hold much meaning. So if we run this log, if we do this log transformation and read on the regression, and if we test for heteroscedasticity in this particular redefined model, well, the p-value from the F test is 0.245, the p-value from the LM test is 0.239. Both of these p-values are quite high. So when you have large p-values, then you don't have enough evidence to reject the null hypothesis. So in this particular specification, we cannot reject the null of homoscedasticity. Or in other words, we tend to believe that the null is true and that there is homoscedasticity in this particular model. So this is one of the more common tests for heteroscedasticity, but this is not the only one. So in the next video, we'll review another test called the white test for heteroscedasticity. So I'll see you there.